In this script, we want to transition from MLP to convolutional neural network. We explain the components of CNN, such as channels, paddings, strides, poolings, and build a standard architecture, a very small LeNet architecture. And then we compare it with MLP that we optimized from last time. So these are the codes from before. I just added an functional. You will see that this basically gives me some like mathematical operation that I can do fine-grained control within custom NN modules. So if you compare this F to NN, NN is like appliances with knobs and memory and states that PyTorch has to remember and move it around. And F is just recipes, and it doesn't have a state. Okay, so that's that. We are still in FashionMnist. Here, it's important to use CUDA or GPU when possible. Here, for example, I'm using the default free T4 GPU in Google Colab. We continue using the normalization and the data as it stabilizes the training. Here, I noticed last time that I was using the train for only the train and test for my validation, which is not a good practice because we want to leave the tests part completely unseen during training and basically hold it out and use the train for both training and validation. Here I fixed that and I'm just using the train for both training and validation. So I'm splitting that. So the rest is pretty much the same as before. And if you remember, we said in MLP, the way that we flatten the image and destroy all the spatial information makes MLP to treat the image as a disorganized bag of pixels, which is really, we are making it very hard. And MLP has to look at the image as its entirety instead of looking at different parts of the image separately. So this makes it very inefficient. There's no weight sharing, as we will see. And it will be brittle to translation. Once an object in the image moves around, the MLP will fail. So with that, let's go on and look at the convolution, starting with some handcrafted kernels. So like I said, we introduced this architecture that is based on this spatial inductive bias that we want to induce to basically has these properties of locality and translation equivalence. A pattern is the same regardless of where it is. And the convolution operation, we showed that it provides this bias. And we use this analogy that the kernel, the learned kernel or a filter is acting like a feature detection, takes a magnifying glass, a small magnifying glass, and this glass is specialized in detecting one specific pattern. And the detector basically slides this magnifying glass across the image, and same weights are used everywhere. It's the same magnifying glass, which is the concept of parameter sharing. Let's first look at some handcrafted kernels. So we want to demo this handcrafted kernels. We need a data loader for that. And let's just choose an image class, image index 7. Probably it's the trouser. So we want a sample image to visualize these features that the kernels are extracting. So let's take a sample image from the data loader. So the data loader normalizes the image, if you remember, and we have to reverse that for visualization and displaying, which brings the pixel values back and for the range that is proper for visualization. Okay, so let's, the sample image is a tensor, right? So let's make a image numpy, the array version of it, and it's basically takes the sample image, and we want to add the mean and standard deviation of the data set that we normalized and with them. Okay, so it will be like this. So we need this image in Pete for visualization of the image, but we have to do the convolution over the tensor, and a tensor of a standard size. And to do that, we have to prepare the sample image for the convolution. And so currently the sample image has a shape of channel H and W, right? And the standard shape for convolution must have the batch size also. And to do that, here the batch size is 1, so we just need to unsqueeze that dimension and then send it to device. Okay, so the image tensor will be sample image, unsqueeze, and send to device. And let's just use some kernels that we discussed in the course. For example, the averaging kernel, right? Which is a blur kernel. Gorge tensor of the same basically values on all the 3x3. Let's work with a 3x3. So it's 1/9 multiplied by 3. Let's we can add more kernels. For example, the famous edge detector kernels, and here, for example, the Sobol operator has this form. Let's just hard code this into our code. So we need Sobol also, and so these are our kernels, and let's do a convolution using them and visualize the features that they are extracting for us. Okay, so to visualize them, let's just make an image. We need a row for each kernel, and then can adjust the fig size. Let's give it a title. Okay, so I'm doing that. I'm going over all of these kernels, and I have to first tensorize the kernel, send it to the device, and do the convolution. So like I said, the kernel has this shape that is standard for the PyTorch convolution. So we have to keep that in mind. Okay, so now with Torch no grad, we want to do the convolution. So the convolution will be like this. We are not using any specific stride. So stride will be 1 and padding will be 1. It means that we just move this kernel one at a time, 1 pixel at a time. And here, by keeping the padding 1, the image will stay the same size. And to basically, let's just call it output tensor, we want to transform this to NumPy because I want to visualize it. And you see that I squeeze CPU NumPy. So now we can do the aim show. And then I want to incorporate, actually, let's first show the kernel, which here I'm using Seaborn heat map. So this will be 0, this will be 1. Then we want to show the output, basically the features that is learned. And we can run this code and see the result. To do that, I'm just running the function. Okay. Something went wrong here. Oh, yeah. I want the kernel NumPy. So the blur is basically a uniform kernel. When convolving over an input of this shape, it gives us a blurred shape. The vertical extracts the vertical edges, and the horizontal extracts the horizontal edges. So with that, let's move on to learning these kernels, starting with the components of CNN, padding and strides, and then we will move on to pooling and then the concept of channels. So I'm gonna write a function, adding no grad. We'll demo the pooling, the padding and stride for you. We want to show how padding and stride affect the shape of an image, right? So assume an image of a 8x8 shape. Let's just make it with a random normal. So like I said, I needed a standard format. So this is a 8x8 image, but the first dimension and second dimension are just the standard that we need, the batch size and channel length. So we can print out the X shape. So we want to compare it with the convol versions. And then the default convolution has a padding 0 and stride 1. So let's imagine that K of size 3, padding of 0, stride size of 1. And this is the code. It's, let's call it convolution, doesn't have padding, takes in one channel, it outputs one channel. Here, in this case, we can, of course, output more. For the time being, we can output one channel, and the kernel size is 3, and the default is P0 and S1. What will be the output? We know how to compute this, right? I mean, we can run this, of course, but let's just talk about the formula because we don't need to test this out for now, and we can compute it easily. I mean, we can test it out for now, but for a large network, we want to know how to compute this. Simplest case is a one-dimensional, where we have a kernel that is sliding over this one-dimensional. What will be the length? It will be input plus twice the padding. Here padding is 0, but that's basically the length. And what's the last index that we can take another k? It's basically this minus k. We have to divide this by the stride length, and then this is the last index that we can put another one, so plus 1. This is the number of output, but maybe sometimes we are getting a non-integer value, so we have to take the floor of this. So here in this case, we have input of size 8, P is 0, S is 1, K is 3, so 8 plus 0 minus 3 is 5 over 1, 5 plus 1, 6. So that will be the output. So we expect a 6 by 6. So this is that. Let's look at, let's play with these values of P and S. The second case, we can add padding here. So what will be the output? So 8 plus 2 minus 3 plus 1 will be 8. Preserves the shape. So let's run this. Let's look at another version where we can play with the stride, right? So far we kept the stride to be 1. So if we do the computation, it will be, so here's stride 2, and let's keep everything the same. So P1, K3. Okay, so if we do the computation, it will be 8 plus 2 minus 3 divided by 2. And if we take the floor of this guy, it will be 4. So we are expecting a 4 by 4. And let's do it. Okay, so let's try pooling. Let's create an imaginary image, and I want to make it deterministic because I want to talk about this pooling operation. So let's make a torch A range, size 4 by 4, so we need 16. And so remember, we discussed 2 different pooling in the lecture. One was maximum and the other one was just averaging. And the reason is we want the convolutions to be invariant to translation. So if we don't do the pooling, it is equivariant, meaning that the feature map shifts if the input shifts. But if we only care if a feature is present, not exactly where it is, pooling can help here because it just summarizes a neighborhood and it makes the network less sensitive to the exact location of the feature. So let's do max pooling first, which is an max pool here at 2 dimensions. So let's keep size 2 and let's keep the stride 2 because this is more intuitive. It means we look at the 2 by 2 parts of the image and we don't have any overlap. So for example, here, in this case of A range, maybe I could print this out first. So let's do it. So here, for example, if we look at the first 2 by 2 here on this part, we expect 5. So let's look at the value, for example, of that corner. So the output is a 2 by 2, and these are the output like we expect. Let's add the average pooling here. So the average pooling, same kernel size and stride, and you see that these are the averages. So like we discussed, max pooling's detector gives out the strongest clue. And this K2S2 is very common. It basically halves the dimension. It's non-overlapping. And we really prefer max pooling because of this preservation of the strongest feature. But average pooling is also possible. The detector is answering this question of what is the general vibe of this neighborhood. That's how we handle the pooling. And then let's talk about the channels, which is really the more nuanced part of this convolution neural networks. So far, we discussed like one detector that uses one kernel, but we can employ several detectors that each one has a different expertise and they use different kernel. And at the end, they can report and maybe even talk to each other to combine their findings, right? Let's demo that. Same deal. I'm gonna make a grayscale random image, meaning that we have one channel, and since we want it to be in a standard shape for our PyTorch convolution, it should have the batch size and the channel size and everything. So let's just stochastic, and then we wanted to have one batch size, say batch size of one channel. It's a grayscale and 28 by 28. Okay, so now if I do the convolution over this guy and I, instead of one detective, I hire 6 detective, right? So in that case, the in channel is 1, it's the raw grayscale. Now channel will be 6. Let's use magnifying glass of size 5 by 5 and padding of 2, for example. So that's the convolution operation, and we can apply this on the grayscale image now. So the y1 will be conv1 over x gray. And you see the output is a batch size of size 1, 6 channels of 28 by 28. And these are basically the features that this kernel basically will be applying on. So far, this is, of course, unknown because we have to train this. We can also, of course, change the result of convolution. And maybe we should do it actually in the second if we pass this result here that we have, which is a 6 channel 28 by 28 to the next layer of convolution. Let's say here I have enough size 6, right? And out is 16. Basically, we are asking each detector to maybe crosstalk. For example, if one of them finds it's an expert in vertical edge, finds a vertical edge in a neighborhood, the other one who is a expert in horizontal edge and finds a horizontal edge in the same neighborhood, when they talk to each other, they can conclude that there is a corner here, and that's a more complex feature. So that's why we are in a more complex kind of discussion here, that now we can hire more experts with more complex expertise than before. So in this case, for example, we can add padding of size 2. Let's just put it here. Let's see. And I kept this, but of course you could change this also to reduce the size. Let's make a LeanIt. At some point was like a state-of-the-art really architecture. Here we will do with some modern flavor or batch normalization. I want to include the number of classes to make sure we have it for the output layers. Let's just simplify everything. So we need a base block. Let's just call it block 1. That is a convolution block. It takes in the grayscale and output like 6 channels. And in LeanIt kernel that was used here was a 5 by 5. And to keep the dimension, we can choose padding of 2. Okay, so let's do it. So conv1. Okay, so this is I don't need this. Okay, so the architecture here that we want to design have a first block of convolution, then we will send this to a batch normalization, and then of course activation here, like ReLU for example, and then we have to pool. So this is the first block, and then let's make another block of this. So twice multiply by 2. Then after that, we're done with feature detection. We can flatten the output of this. So flatten, and then 3 layers of MLP or fully connected MLP. So that's our plan. We want to do this. Okay, so that's the first block that returns 6 channels of the same image size. We need batch normalization. So you will see that I will have the ReLU. I will use a F ReLU later during the forward, so I don't need to specify it here. Okay, so we will keep the standard kernel size and stride, and the second block takes in 6 channels output of this guy and returns 16 channels. Okay, so here padding, if padding is 0, this will shrink the image. So like I said, these 6 channels now interact or crosstalk, meaning that in this layer, the kernels are really 3-dimensional, a 5x5 kernel and a 6 channel. So it's like a 3-dimensional kernel. So we should be careful about how we are interpreting this. So they look across all 6 input channels, and simultaneously they're looking at all these 6 input channels and sum the result. This combines the simple feature from block 1 into a complex feature in this block 2. Okay, now let's do the max pooling. Same default, and then of course, like I said, I'm just making the blocks here. Later I will need them together in the forward. Then we need the MLP classifier head, which will be 3 layers. So the first layer is basically flattening the 16 by 5x5 size images and 120 hidden neuron. Then we pass this to the next 120 to 84, and then the last one, which is 84, to the number of classes. So these are the logits that we want. Let's also call the initialization of the weight. We have to define the function, of course. Here we are using k-mean normal. We can use this for both linear and non-linear convolution. And here, this is how we initialize the weights. And if bias is not initialized, we can do that too. Here I just put 0. Okay, let's write forward. Forward is basically taking in the first block x, and then batch norm, and then notice that I'm using ReLU using F, and then self pool, and then the next block, basically same thing. And then we can flatten, we get a view of x that is flattened, and then we can send it to the forward layers or the MLP head. This will return the logits. That's it. Okay, so I want to train both the MLP again and CNN, and I want to compare them. So let's write a function that basically does the job for us. I'm still using the same loader, so I need a train loader and validation loader, and I have to choose a epoch. Let's just go with 10, and then learning rate and the weight decay for our optimizer, which here I'm planning to use Atom. So with that, let's do it. I want to specify my MLP config because if you remember, we wrote it in a way that to come up with the best architecture. Here, let's just pick up one of those architectures that work well. We don't need a configuration setup for the LeanNet CNN. It's already there as default, but I'm gonna make a config dictionary to basically iterate over it and train and then populate the histories. Okay. So configs, I need histories for both that later during the loop, I will populate them with the history of each model. And the criterion will be cross entropy for us. And then here for each model, let's just call this setup. The model will take in the name of the model and the setup. We send it to the device. Here is the same optimizer for both. And then for each model, let's just populate the accuracy. And before training, let's just return the number of parameters of each model. How can they fare depending on their size? So let's report the number of parameters. Okay, so we have MLP with 135,000 parameters and CNN about 62,000. CNN is using this weight sharing that we said. The same kernel is reused across the entire image. Even despite that much less number of parameters, it performs more complex spatial operation, as you will see. Okay, so let's go back to the training script. So for epochs, So we want to train one epoch, the function that we wrote from before, and then evaluate, and then append it to the history. We can also print the progress. So we've done this before. I'm just going to repeat the same thing. So that's it. This is really the script. I just need to fix this indentation, and that's otherwise all good. Okay, so this is how we are running the training. So in the meantime, let's just write a few plotting scripts to investigate the learned features and do the comparison between the training accuracy over the epochs. And then we can also check if the networks are robust to translation, meaning that if we move an object in an image, we expect the model to give us the same classification result. Okay, so here is the result. As you can see, we were expecting CNN to achieve a higher accuracy, but notice that it can do it very, very early on, even though the number of parameters is much less. It has a higher capacity, which is interesting. And it's basically because of the fact that the inductive bias forces it to learn meaningful spatial features. Okay, and here is the next experiment where we are looking at these layer weights in the first layer. And as you can see, and we've seen this before, the MLP first layer weights are really noisy global patterns. But for CNN, we have these 6 structured local feature kernels that are finding these structured and local features. Here, for example, for this trouser image, we see that how these features are extracting what they are expert in, which are really meaningful and shows clear structure like edges, gradients, corners, while they are still local. And here's a translation test where we are shifting the image a little bit, and we see that here the MLP correctly identify this as shared, but with a small shift it misidentify it. Same with other examples too. That means that how brittle is MLP. We are looking at CNN. We still see some misclassification, but it's much rare. And here, for example, you see that shifting the bag and trouser doesn't really break the CNN. Later we will see that we can do much more with CNN. We can improve the LeanNet architecture significantly with the updates that we will talk about. And also we show that if we go for a deeper architecture, we can achieve a very good performance.